Welcome back, design junkies. If you enjoy the podcast, let us know with a like, a follow, or a comment. A&D. Get ready for mechanical engineering made simple. Okay, let's get into it. Today we are diving deep into the really complex world of axial turbomachinery.
We're talking about the core principles here, what makes turbines, compressors, and fans actually work.
And our sources for this deep dive really take us on a journey. We start with these, perfect, idealized, two-dimensional theories.
And then they throw us right into the deep end, straight into the messy realities of three-dimensional flow, instability, all of it.
That's the real story here, isn't it? This core conflict. You start with these clean, simple assumptions to get a basic design.
You have to. It's the only way to begin. But those assumptions, they have a very short shelf life.
They break down almost instantly in a high-performance engine, and then designers are forced to grapple with these really tough problems: flow separation, stall, huge pressure changes from the root of the blade to the tip.
Right, the perfect model gets you started, but managing all those imperfections, that's what makes the engine actually perform.
So to set the stage, we're talking about a standard setup, right? A stator, which is
It's the guide vanes or nozzles, yes?
Yeah.
Followed by a rotor, the moving blades,
And the key metric we're tracking is specific work.
which is really just the drop in total energy, the stagnation enthalpy across that stage.
And that energy transfer immediately creates a divide. In a turbine, the flow is accelerating. It's being pushed along.
Which makes it inherently more stable, less prone to losses.
But a compressor is the exact opposite. You're fighting the flow, decelerating it. It's a diffusion process.
It's an aerodynamic nightmare, really. That's why compressors are so vulnerable to stall and massive pressure loss. And that one difference dictates, well, pretty much every design choice from there on out.
Okay, so let's start in that idealized world, the two-dimensional flow model.
The foundational approach, really. You have to start somewhere simple. So the idea is to look at the pitch line, the mean radius.
And just assume the flow conditions there are the same everywhere else.
Exactly. You just assume it represents the whole flow, which is, only remotely reasonable if the blades are short compared to the machine's radius.
So we're already ignoring a lot of reality near the hub and the casing. But how do we even judge performance in this simple model? We need metrics.
We do.
Yeah.
And we lean on two main types of efficiency. First is total-to-total efficiency.
Okay.
Think about the core of a jet engine. This metric is critical there because the kinetic energy leaving one stage isn't lost. It's fed directly into the next stage and recovered as pressure.
So the energy is conserved and passed down the line. What's the second type?
That's total to static efficiency. You use this when that exit kinetic energy is just gone, dumped to the atmosphere.
Like the last stage of a power turbine or an exhaust fan?
Precisely. And by definition, it's always a lower efficiency value because you have to count that dumped energy as a loss.
What I find fascinating is that even for modern preliminary design, the sources point back to these almost ancient tools, like Soderberg's correlation.
It feels like it should be in a museum, doesn't it? Developed from steam turbine tests decades ago.
But still relevant.
It is, and that says so much about that early empirical work. Soderberg's method, it calculates loss based on how much you turn the flow and the geometry. It captured the basic physics of friction and turning so well that it still gives you a fantastic first estimate.
A quick way to get maybe 80% of the way there before you fire up the supercomputers?
Exactly that.
Okay, another fundamental concept we have to cover is the reaction ratio, R.
Right. This is all about where the work is happening in the stage. Reaction is the ratio of the static pressure change in the rotor compared to the static pressure change across the entire stage.
So it tells you how the work is split between the moving blades and the fixed ones.
Perfectly put.
Let's look at a couple of key design points for a turbine. What happens when R equals 0?
That's a zero reaction stage. It means the static pressure is the same at the rotor inlet and outlet. All the pressure drop happens in the stator, in the nozzle.
And the rotor is just changing the fluid's direction.
Purely extracting work from the velocity change.
Now, the sources were very clear that this is not an impulse stage. That was a bit confusing.
It's a subtle but really important distinction. An impulse stage is a design goal. The aim is zero pressure change. But in the real world, because of friction, you always get a tiny increase in enthalpy across the rotor.
So for a true impulse design, the reaction ratio R is actually a small negative number.
That's it. A zero reaction stage is just where we measure the static enthalpy change to be zero, ignoring that little friction effect.
Got it. Okay, so what's the more common balanced design choice?
That would be the 50% reaction stage where R equals 0.5. This gives you a nice symmetrical velocity diagram, and crucially, the nthly drop, the work, is split evenly between the nozzle and the rotor.
And regardless of the reaction, the main goal in a turbine is always the same: avoid diffusion at all costs.
Absolutely. You are accelerating the fluid. If you let that velocity decrease even a little, you create an adverse pressure gradient. And that, with the high turning angles, is just begging for the boundary layer to separate.
Like catastrophic losses.
Massive losses. A turbine is built for speed, for acceleration.
Which brings us to the compressor, where we have no choice but to do the opposite. We have to decelerate the flow to build pressure.
And that's the whole challenge. This forced diffusion is why compressors are so prone to loss. And it's why a jet engine needs way more compressor stages than turbine stages to get the job done.
I assume the 50% reaction design is popular here too.
It is. Often it's the top choice for efficiency.
Why does R equals 0.5 work so well in a compressor?
Because you're sharing the pain. You're splitting that difficult adverse pressure gradient evenly between the rotor and the stator.
So you don't overload one row and cause it to stall?
You're distributing the risk of boundary layer separation.
Yeah. Speaking of risk, we have to talk about the big villains of compressor instability: rotating stall and surge. What's the difference?
They're very different beasts. Rotating stall is less catastrophic, but it's still really dangerous. The blades don't stall all at once. It happens in these discrete patches that, well, they rotate around the annulus.
So parts of the engine are choking in a wave that travels around the machine.
Yes, usually at about half the rotor speed. The big problem there is that it creates these cyclical loads on the blades, which can lead to fatigue failure. But the total mass flow through the engine stays steady.
And then there's surge.
Surge is the one that keeps engineers up at night. It's not a rotating patch. It's a massive, violent axial oscillation of the entire flow. The whole flow field can break down and even reverse direction for a moment.
That sounds destructive.
It can be. It can destroy an engine if the control systems don't catch it instantly.
So how do you fight these things? I read about an early technique called casing treatment.
Right, using grooved casings, often with skewed grooves, right over the rotor tips. The idea was to delay the onset of stall.
By stabilizing the flow near the outer wall.
It helps re-energize that sluggish boundary layer fluid near the casing. It was most effective against what we call wall stall, but there was a catch.
An engineering trade-off.
Always. The grooves themselves create more friction and mixing, so you take a hit on overall stage efficiency. You gain stability, but you lose performance.
So what's the cutting-edge approach now, controlling these things before they even start?
It's all about active control systems. One method is active feedback control. You place these tiny sensors, like hot wires, in the flow to detect the very first hint of a disturbance.
And it's still incredibly small.
Exactly. And then you use individually actuated vanes, tiny, super fast flaps, to generate an opposing disturbance that cancels out the first one. You kill the instability before it's born.
And the other strategy, aeromechanical feedback.
This one is just beautiful physics. You have a chamber with high-pressure air and these little flexible reed valves. If a disturbance causes the local flow to slow down, the static pressure there rises.
Right.
That higher pressure pushes on the reed valve, which opens and injects a jet of high-momentum air right into that troubled spot. It uses the problem, the pressure rise, to trigger its own solution.
That's brilliant. And all this talk of instability just brings us back to the limits of that 2D model we started with. It completely fails when the blades get tall.
It does, because with tall blades, you get significant radial velocities. The flow starts moving up and down the blade span, completely redistributing the mass flow. The physics at the tip can be totally different from the physics at the root.
So we need a better tool. And that brings us to radial equilibrium theory.
A way to handle that span-wise variation. But it still has a couple of big simplifying assumptions. First, any radial flow has to finish inside the blade row. And second, the flow outside the blades is perfectly smooth and uniform in a circle.
And when designers use this, they often choose something called free vortex flow. This is where the name is a bit misleading, right?
It is. Mathematically, it's where the product of the radius and the tangential velocity, so r times c sub q, kept constant. But a more accurate name would be vortex-free, because it results in zero axial vorticity. It's a very clean, ideal solution.
And the design benefit is huge.
Oh, it's very attractive. You get uniform work done at all radii and a constant axial velocity. It makes everything much simpler to calculate and match between stages.
But there's a cost.
A big one. To maintain that free vortex condition, you need a lot of twist in the blade from root to tip. That's expensive to manufacture. It also tends to create really high Mach numbers near the blade tip, which hurts efficiency.
So to avoid that cost, sometimes they just don't twist the blades.
Exactly. That's the direct problem. You hold the flow angle, alpha, constant with radius. It's less aerodynamically perfect, but much cheaper to make. A classic design trade-off.
And even this more complex theory has its limits. The experiments show that this equilibrium isn't all contained neatly inside the blades.
No, a lot of that flow redistribution happens both upstream and downstream, which led to the next step up in theory, actuator disk theory.
This one sounds like pure math. You shrink the whole blade row down to a single plane.
That's exactly it. You treat it like a discontinuity, an actuator disk. It abruptly changes the swirl, but the axial and radial velocities pass through continuously. It's a way to model the interactions between closely packed stages.
And this gives us two key rules.
Right. The mean value rule, which says the axial velocity right at the disk, is the average of the velocities far upstream and far downstream. And the settling rate rule,
What's that one tell us?
that any disturbance decays exponentially as you move away from the disk. This is so important because it proves that the flow fields of closely spaced blade rows strongly influence each other.
Okay, before we get to modern computing, there's a really unique case study here. The Wells turbine.
The Wells turbine is a fantastic piece of engineering. It's an axial turbine used to get energy from oscillating sea weights.
And its trick is that it uses uncambered, symmetrical airfoil blades set at a 90-degree angle.
Right. And because of that geometry, as the air rushes in and out of the water column, the turbine keeps spinning in the same direction. It generates positive power from bidirectional flow.
Which is just genius.
And the newer versions are even smarter. They use self-pitch control blades. They pivot just a little bit near the leading edge, which helps them produce much more torque and efficiency than the original fixed blade designs.
So, as useful as all these theories are, modern design really depends on CFD, computational fluid dynamics. How do these tools fit together?
The CFD is absolutely essential. It lets you model all the complex 3D flows we've been talking about. But, and this is a huge charm, but CFD does not replace good preliminary design.
So if your basic one-dimensional math is wrong, CFD won't save you.
It won't fix a bad concept. If your stage loading is wrong, CFD will just show you a very detailed picture of your bad design failing. It's a refinement tool.
A tool to exploit the 3D flow, not just fight it.
Precisely. We can now design things like bowed blades and turbines to control secondary losses, or use sweep-in compressors to reduce corner separation. These are techniques that were impossible without CFD, and they work with the complex flow.
Let's end on the root cause of all this complexity. Secondary flows. What's happening there?
It's an inevitable consequence of turning a rotating flow. Think of it like a gyroscope. When you try to turn the fluid's existing vorticity with a blade, it creates this secondary swirling motion.
And that's worse near the walls.
It's strongest there because of the boundary layer. This swirling leads to localized overturning and underturning of the flow, which wastes energy and, crucially, is what promotes stall right at the blade ends. It's the very reason we have to abandon those simple, elegant 2D models.
Which brings us full circle. From this perfect uniform flow ideal to the practical reality where every single radius has its own complex story. It shows that engineering is that constant negotiation between the clean concept and the messy physics.
That's it perfectly. It's a process. You simplify to get the basic size and shape, then you bring in the complex 3D tools to manage all the unavoidable instabilities and losses.
Which leads us to a final provocative thought for you to take away. In highly loaded modern compressors, the work done factor, we call it lambda, it actually decreases as you go through the stages, dropping to maybe around 0.86 later on. So considering all this 3D complexity, what happens to that miscalculated energy when the flow isn't uniform? And how does that uneven energy distribution affect the life and health of the downstream stages? Something to mull over.
We hope this deep dive gave you a fast track to understanding the fluid mechanics of turbomachinery.
And if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.